So these units, I don't think they really need any explanation. Except maybe ohm meter. That's kind of a weird one. So resistivity is ohm meter. The formula involving resistivity is resistance equals resistivity times length over area. And this is resistance is ohms, and area is meters squared, length is meters. So in order to get ohms out of this, first we've got meters on top, meters on the bottom, so this will cancel. We've got meters on the bottom. And so this multiplied by these two things together, which basically have the unit of 1 over meters, we need to get the meters to cancel out and have ohms. So this has got to be ohms meters. And maybe I should let me do it this way. I'll just do units here. Ohms equals resistance times meters over meters squared. So I've just got units. I don't actually have the variables. So like I did earlier, those are going to cancel out. I'll multiply both sides by meters. Now that cancels out and I'm left with resistivity equals meters ohms, or ohms meters. Number 9. Oops. Wish there was somebody could say, hey, I can't see the bottom. The direction of the current is opposite the direction of net electron flow. Yes. Apparently, according to Ben Franklin, he's the one who decided that current would flow out of positive parts of batteries and into negatives. So wherever you see the positive, that's where the current comes out, and then it goes in. So it flows from positive to negative. In reality, it's going the other way. Electrons go this way. If we're talking about current through wires. If we're talking about a solution or something else, you can actually have current that's positives flowing around. But it's opposite electron flow. Same as proton flow if you had proton flow. Number 10, potential difference across the resistor is doubled. So this gave some people trouble. V equals IR. Or I could say I equals V over R. If you double the resistance, if you double the potential, then this has got to be twice what it was before. And that's because resistance, we're assuming for this test, unless we say otherwise, resistance is constant. Resistance is based on something's resistivity and length and cross-sectional area, and that's not going to change. So if you have a circuit and you double the potential, you bump up the voltage to twice what it was before, that's not going to change the resistance. So it has to change the current. So if you multiply this side by 2 by putting in 2V, then you've got to multiply that side by 2. In this case, we've got 3 identical light bulbs represented here as just resistors, and this one burns out, so you remove that. So what's going to happen, since these are in parallel, is that the voltage across these two is not going to change, because the voltage in parallel across each resistor is equal. These are all equal, and in this case, since this is the only resistor, it's equal to the source voltage. So when this burns out, the voltage drop here does not change. The resistor does not change. And if the voltage drop and the resistance do not change, then current doesn't change, because V over R doesn't change. So if the current doesn't change and the resistance doesn't change and the voltage doesn't change, nothing's changing. This is the same bulb doing the same thing. So, and same with this one. The voltage of all 3 of these is the same. Removing that one doesn't change anything. They're still in parallel, so nothing changes. Light intensity is going to remain the same. Light intensity is based on at least one of those things, and nothing's changing, so light intensity won't change. The power, formula for power here, there are three formulas for power, but if you know that VI equals power, this is the voltage, this is the current, which is I, just multiply these together, and the one with the most watts is that one, appliance number 3. To measure potential difference across a resistor, a voltmeter is connected in parallel because it has the same potential difference across it as the resistor. So if you've got, it would be like this. Back to this diagram. If, let's say, in the beginning, we just had 2 resistors in parallel, and I wanted to measure the voltage from this point to that point, the voltage drop from one location to another, I could put in this thing right here could represent my voltmeter. And adding that in parallel does not change the voltage across these two, and the voltage that across this is going to be equal to those. So that's why I put it in parallel. Now if I stuck the voltmeter in here from there to there, then the voltage drop is going to be different. I've got it in series now, so it won't necessarily have the same voltage drop as these other things next to it. So you put it in parallel so it'll have the same voltage drop. Ohm's law is V equals IR, so some version of that you can do I equals V over R, and you could do R equals V over I, but these other ones must be wrong because that one's right. Ohm's law, this is Ohm's law shown as a graph. If you increase the voltage on a resistor, then the current goes up. And unless it's a non-ohmic thing that does not obey Ohm's law, you're going to get a constant slope here. It's kind of weird. I equals, so let's see. If I mess around with this formula, if I do I guess I can mess around with this. I over V equals, I'm just dividing both sides by V, and then I guess I have to divide both sides by R. So 1 over R equals I over V. So the slope of this is I over V, which is 1 over R. So it's this is sort of like, this slope gives us an idea of what the resistance is, but it's the reciprocal of resistance. At any rate, there's a directly proportional relationship between how much voltage you put in and the amount of current at a given resistance. The resistivity of a conductor depends only on the specific material. I think I wrote the formula before, but I'll write it again. The resistance, which is not resistivity, equals the resistivity times L over A. So this is resistivity, this is resistance, this is ohms, this is that ohms meters thing I talked about on the first page. And that's just dependent. So silver has the lowest resistivity. Copper has a pretty low resistivity. Aluminum has a fairly low resistivity. Apparently damp wood has a somewhat low resistivity, and things like rubber and foam have high resistivities, and a vacuum has a very high resistivity. Current is a measure of the amount of charge that moves past a point per unit time. So that formula is, I still don't know about that delta, but anyway, I'll put it in there. Q is charge, T is time, and if you think of a pipe with a little gate on it that measures how much is flowing past that gate during some time period, that's what current is. The problem with this analogy is that since it's how much charge flows by here, you could have little charges flowing by fast, or you could have big charges flowing by slowly, and you'd still have the same current. 18, if the resistance of a resistor increases, the current through the resistor will. Well, so here's Ohm's law. If you increase resistance that's in the denominator, then this number is going to get smaller. So current will decrease. Number 19, circuit consists of battery and 2 resistors in parallel. With the battery and the third identical resistor, in parallel with the battery, and a third identical resistor is added in parallel, the current in the 2 initial resistors. So this is the reverse of this other one. This is saying, first we have this is in parallel, and then we add another one. And that's still not going to change the voltage across here, and it's not going to change anything that's happening there. Since it doesn't change the voltage, doesn't change this resistance or this resistance, it's not going to change the current either. So the current in the 2 initial resistors will stay the same. What will change is the total current. So if you think of charge flowing through here, draining from this side to this side, the more paths it has that it can go across, the more total current's going to go across. So this current here and here, that's going to change in this diagram. And like if you remove that resistor, that current decreases. If you add it back, this current increases. Sort of like plugging up a hole, making a new hole, a new way for current to get across. Number 21, this is a good test. You remove one bulb, and if the rest of the bulbs stay lit, it's parallel. If the rest of the bulbs burn out, it's series. Or go out, not burn out.